Hello students, welcome to IMS Academy. In the foundation course, I started the subject of electronic devices and circuits. In that subject, I started the chapter of semiconductors, but I was given 10 hours for this subject. But all the 10 hours I would like to explain semiconductors. Every student is going to get satisfaction after the completion of these electronic devices, semiconductor topic I can say in the electronic devices. Understand that? Yes, Pragyabat. Hi, sir. Yes. Hello, Pragyabat. Good afternoon. Yes, now I started already in semiconductors, conductors and insulators. I did now. In this session, I would like to explain semiconductors, but how that semiconductor will be useful, where it is used, and what are the parameters you can have, and how the problems are to be done by using those parameters. One by one we can discuss. Wherever the analysis is required, that I will do perfectly. Every student will get satisfaction, no doubt. Understand? Yes. Yes, before starting the subject, I would like to give some information regarding the IMS Academy. The students who are willing to take the admission for GATE in IMS Academy, when you want to take the admission for GATE 25 and 26, you can make a call to this number. You will get every information regarding the GATE. And if the student joins in IMS Academy, what advantages, what benefits they will get? That's given here now. The program features are given here now. Online and offline coaching will be given by the IMS Academy to the students only now. 800 plus, that means more than 800 hours of live classes with the live interaction is possible now. More than 800 hours live classes. But IMS Academy provides theory book, exercise book. The exercise book contains more than 4,000 questions. In that exercise book, it is given level 1, level 2, level 3 questions. The students are in a position to do the questions of level 1 and level 2. Easily they can crack the GATE. Level 3 also not required. If any students wants to go for the engineering service examinations, at the time it is required level 3 also. The student is willing to get the more knowledge on the subject, more grip on the subject, they need to do the level 3 also. So all three level questions are given in the exercise book. No need to prepare any other textbooks. Only these questions are just now, because around 4,000 questions, more than 4,000 questions given in that book only now. And also GATE question banks will be provided by the IMS Academy to the students only now. But in the GATE question bank, more than 34 years GATE questions were solved. But every GATE question was solved. And also alternative solutions also given for some questions, and also given video solutions also for certain questions only now. Easily students can understand how to tackle the GATE questions. Understand? 12 personalized one-to-one mentorship sessions possible here now. This one-to-one mentorship means the students wants to have any preparation strategy you think it's so. They can directly discuss with the faculties. That's why my plan session is there now. 12 my plan sessions will be given to the student. Each and every month, one my plan session they can take from the mentor, and they can get the right information. And they can understand how to start the preparation, and what are the subjects initially it is to be started, how many hours they need to spend. These are all discussed only in the mentorship session only now. But more than 130 online tests with video solutions of the mock test and many more possible in IMS Academy. So don't delay. If you are willing to take the admission in IMS Academy, immediately you call to this number and get the right information. All will give all the information you will receive from the our members only now. Understand my word now? Yes. Now I can start this subject. But in this session, I would like to explain semiconductors. Semiconductors. This is very important. But I would like to start semiconductors. Semiconductors. But after the advent of semiconductors, there is a wide change in the electronic field. Wide change only. Lot of changes it came. Just to go before the entering of the semiconductors, we used only vacuum tubes, vacuum diode, vacuum triode, vacuum pentode, vacuum tetrode, thyratron, like that devices were used. They were all outdated nowadays. But in the olden days, you watch on radio, the size is a very big size. But when it is operating for 2 or 3 hours continuously, the temperature is going to increase more and more. The reason behind it is vacuum tubes are going to consume more amount of the power. The frequent shutdown also required. The device is the frequent shutdowns are required to cool down the what now? That components only you can say now. But after the advent of the what now, the semiconductor, what happened? The vacuum diode is replaced by PN junction diode or crystal diode. The triode is replaced by transistor BJT. Thyratron is replaced by thyristor. Lot of advantages only now. The power consumption made by this device is very, very less. Very less power consumption is done by the semiconductors. And also reliability is a more by these devices. So where we are using the semiconducting devices, laptops, any laptop is there means, there what now certain devices are designed with the semiconducting materials only. CPU, the CPU with semiconductor devices only now, that can operate the personal, that operates the computer only now. And next one is nothing but the what now, we are using the so many advantages now. Even in the what now, refrigerators also they are using. Even in the washing machines we are using the semiconducting materials. Like this, so many applications are there now. Understand my point now. But the next one, even in the mobile phones also we are using the semiconducting materials only now. All the mobile phones are with semiconducting materials only. That is why a lot of change it came in the electronic field because of the advent of semiconductors, I can say now. So we can discuss about the semiconductor. Understand my point now. But I explained what is insulator in the last class. The material which doesn't allow electrons to pass through it is called as an insulator, I said. And also I explained about the conductor. The material which allows electrons to pass through it is called as a conductor, I said. What about the semiconductor? They are only given semi. The semiconductor means the material which can act like an insulator and conductor is called as a semiconductor only now. The material which behaves like an insulator and also behaves like a what now, conductor only now. That is a semiconductor only now. So how, when it can what now, act as an insulator, when it can act as a conductor, it depends upon the temperature only. Suppose the temperature is maintained 0 Kelvin, you think it so. At the time we cannot find any flow of current in the semiconducting material. At the time it can act as an insulator. Just like an insulator it can act, the semiconducting material. Whenever you are giving temperature, room temperature is maintained, you think it so. At the time the semiconducting material can act as a what? Conductor only now. That's why the change of temperature can make the material to act as an insulator and conductor. That is why it is given a name semiconductor only, you can say. So the definition I can give like this: the material which lies, the material which lies between the properties of insulator insulator and conductor is called as semiconductor. This is the semiconductor, is called as a semiconductor. Generally we are using what material as a semiconductor? Generally we are using germanium and silicon. These two materials are used. But most practically we are using the silicon because there are certain advantages because of the silicon. But as compared to the germanium, those points I will discuss later. For the time being, I can say the germanium and silicon are the fundamental semiconducting material we are using in the design of the PN junction diode, in the designing of the transistor, in the designing of the FET. We are using germanium and silicon. These two materials we are using only. Understand my point now? But most practically we are using silicon, we said no. But a germanium or silicon, if it is taken, they are the fourth group elements. What group elements they were all? They belongs to which group? Fourth group element only now. What is fourth group element? An atom which contains 4 valence electrons is said to be fourth group element only. There is an atom that contains valence electrons 4, then we can say it is a fourth group element only now. The valence electrons are existing 4 means germanium contains fourth group only now, fourth valence electron. Silicon also contains 4 valence electrons only now. That is why they come under fourth group elements only now. But energy band diagram, suppose you have taken energy band diagram. Suppose I have taken energy band diagram like this. The energy band diagram of germanium or semiconductor, I can draw like this. This is the energy band diagram of semiconductor. I can write energy band diagram it is. Energy band diagram. But in the last class I explained this is said to be valence band. This is said to be valence band. The band which contains number of valence electrons is said to be valence band, I said already. This is said to be conduction band, I said in the last class, I explained. The band which lies above the valence band is called as a conduction band. I said already this band is nothing but the forbidden energy band or forbidden energy gap also we can call forbidden energy gap. Suppose I maintained room temperature. Suppose I maintained 0 Kelvin. Initially 0 Kelvin I maintained. If I maintain 0 Kelvin, I said just now, the semiconducting material can act as an insulator, I said. But why it is acting as an insulator? What phenomenon is done inside of this energy band diagram? I would like to explain certain points you will understand clearly. At 0 Kelvin, what is going to happen? All the number of electrons are going to exist in the valence band. All the electrons are existing in the valence band at 0 Kelvin. That means what now? The semiconducting material structure, if it is taken, band energy diagram, if it is taken, this band and bond energy, band theory and bond theory is there now. The band theory, what I can explain, suppose I selected germanium or silicon, I have taken silicon atoms, I have taken here now. This silicon atom is connected with one more silicon atom here. And one more silicon, number of atoms are existing in the material. number of silicon atoms are existing. Whether it may be a germanium or silicon, it doesn't matter. And one more silicon I have taken here now. This is one more silicon. Still this will continue this side and this side and this side. It is going to continue this side and this side. It's just now, this is a bond theory. This is nothing but the band theory. It is nothing but the bond theory. What is that bond theory says? Silicon is a fourth group element, I said. It contains 4 valence electrons. Silicon contains 4 valence electrons. These are all the 4 valence electrons of the silicon. This silicon can contain 4 valence electrons. This side 1, this side, and this side 1 more electron here, this side. This side 1 and 1 more this side, 1 more this side is a 4th. Here also 1, this side 1, this side 1, this side. Like that, what happened now? Electrons can be arranged in the bond. Now try to watch here now. This silicon valence electron here existing. This silicon electron is existing here now. These 2 valence electrons are going to be shared. Sharing of the electrons will be done here now. Due to sharing of electrons, a bond is created. What bond is created? Covalent bond is created only now. You know very well, the covalent bond is formed by the sharing of electrons. Ionic bond is formed by the transfer of the electrons. Mostly possible now. But here the sharing of electrons is done. This atom shares this electron, this atom shares this electron. Then a bond is created. The bond which is formed here, formed in between these 2 silicon atoms is nothing but the covalent bond. Covalent bond is formed. Covalent bond. Like that, what you can say, these 2 electron of the this silicon here, these valence electrons will be shared. They will be forming the one more covalent bond. Finally, 4 covalent bonds are formed here like that. 2-dimension view I gave it now. When the bond is formed, electrons can move easily. They cannot move easily. They cannot move easily. But all the number of electrons are existing within the bond only. Within the bond, they are unable to move only now. Now the point what you have to remember, electrons are within the bond. What bond? Covalent bond only now. But the valence band you got, all the electrons are within the bond. What bond means? Valence band only now. One more way you can define. One more way you can define in the energy band diagram. Germanium and silicon, you take it here now. Germanium contains, silicon contains how many number of valence electrons? That's very important point first. Based upon the atomic number, you can arrange the what now? We can explain the what now? Band theory only here now. Now the point what I wish to say, suppose, the next one what I wish to say, suppose I have taken silicon for example, because most practically we are using the silicon. But in the diagram you watch last one you please watch. If you watch the last diagram, there is a forbidden energy gap. The gap is existing between the valence and conduction band only now. These bands depends upon, the band energy depends upon the force of attraction from the nucleus only. If the force of attraction between the nucleus and valence electrons is a very strong, you think it's so, at the time the energy band diagram will be wide possible. If the force of attraction is a less, you think it's so, the force of attraction is a less, the gap will be reducing only, we can say. So that is why I wish to explain, germanium contains how many number of orbits, silicon contains how many number of orbits. Finally, where we can find what now forbidden energy gap of the more you can understand clearly only now. Just now I said, the first orbit nucleus you got, there is a first orbit. The first orbit and second orbit you have taken means the gap is a more possible. Forbidden energy gap is a more possible. Second and what now first and what now second and third if it is taken, reducing the what now? Reducing the what now? Forbidden energy only now. That means orbit level is increasing more and more. The forbidden gap is going to be reduced more. The reason is attractive force from the nucleus will be decreasing with the increase of the number of orbits only now. Based upon that concept only, energy band diagram, we can explain. Now clearly you will get the clarity you asked. Suppose I selected here, just 1 minute. Suppose I selected here silicon. Silicon atomic number is nothing but 14. Atomic number is 14. Atomic number is 14, you know. Atomic number of the silicon is 14. The 14 means how the arrangement of atoms will be made. Suppose I selected here. This is the orbit. Second orbit, one more orbit I have taken for example. And one more third orbit I have taken for example. But certain number of orbits I have taken like this only now. Certain number of orbits I have taken here for example. But orbits I have taken now, 3 orbits for example now. But the point what I wish to say, how many number of electrons occupied by any orbit is calculated by one formula. That formula is nothing but the 2n square, you know very well. Number of electrons stuffed in any orbit is determined by 2n square, you know very well. 2n square. N equal to first orbit, n equal to second orbit, n equal to third orbit. If the atomic number of the silicon is a 14, the first orbit can accommodate how many number of electrons here? N equal to 1, 1 square is a 1, 1 into 2. 2 electrons are occupied in the first orbit. The nucleus for example. Don't consider these lines just formed only now. 2 electrons are occupied in the first orbit. Now you try to watch the nucleus force between the attractive force between the nucleus and the what now? Electrons in the first orbit is very strong. Because these are the electrons are being very close to the nucleus. At the time attractive force is very strong we can say. But next one, second orbit you take it for example, n equal to 2. 2 square is a 4, 4 into 2, 8. The second orbit can accommodate 8 number of electrons. 1, 2, 3, 4, 5, 6, 7, 8. So all these 8 electrons are occupied. First and second, next orbit now. Next orbit is somewhat distance from the nucleus. Somewhat distance. Second orbit is somewhat distance from the nucleus only. At the time attractive force between the nucleus and electrons. Here, this attractive force is strong. Our nucleus and second electrons in the second orbit are very strong. That means the force of attraction between the nucleus and electrons existing in the second orbit will be somewhat less. It is somewhat far away. That means out of 14 electrons, 10 electrons are occupied in the what now first orbit and second orbit, and the rest of electrons are nothing but the 4 still left. Those 4 electrons will be in the third orbit. 1, 2, 3, 4. These are all the 4 electrons are said to be valence electrons. These are all said to be valence electrons only now. These are all the valence electrons are going to create lot of variation in the properties of the material only here now. Now n equal to 3, n equal to 3 means 3 square is a 9, 9 into 2, 18 electrons it can accommodate. But in the atomic number of the silicon is a what now? 14 only. Here third orbit can accommodate only 4 electrons only now. Now please watch. This nucleus is there now. These are the valence electrons, you got it now. The attractive force between these two will be reducing as compared to the what now? Other orbit levels only we can say now. For example, I have taken the germanium for example. You will get the clarity clearly. Where forbidden is good. That means forbidden energy gap from here to here is a some distance only possible now. For germanium, if it is taken here now, its atomic number is atomic number of germanium. I am putting now. Atomic number of the germanium is given as, you know very well. Just a minute, I will give down. Yes, atomic number of the germanium is given as 32. 32 it is required. But how it is going to accommodate electrons, to please watch. How it can accommodate electrons, I will give clearly now. I plotted one circle here now first. The small circle I have taken first. And second one I have taken here now, this second orbit. One more third orbit I want to use. The third orbit I have taken here now. And also I selected one more orbit also. One more orbit I have taken for example. Like that 4 orbits I selected here now. But how it is accommodated, you watch now. 32 means 2 electrons are occupied in the what? First orbit. You know the first orbit can accommodate 2 electrons. Yes, 2 electrons are existing here. N equal to 1, n equal to 2, 2 square, 4, 4 into 2, 8. 8 electrons are accommodated here now. Yes, 8 electrons are accommodated here now. 4, 5, 6, 7, 8. I selected the third orbit. 3 square is a 9, 9 into 2, 18 electrons it can accommodate. 18 electrons. But instead of drawing directly, I am putting the number here now best. 18 electrons occupied here now. Third orbit. So 18 plus 2, 20, 20 plus 8, 28. 28 means 32 minus 28, only 4 electrons still left. Those 4 electrons will occupy in the last orbit, 4th orbit. These are all the valence electrons, so you know. Now you please check one point. Forbidden energy gap in the energy band diagram, forbidden energy gap existing in germanium is more. The forbidden energy gap existing in the silicon is a more. You please try to identify. The forbidden energy gap is how you can understand now. This is the nucleus and the valence electron. The valence electron here what happened now? Somewhat close as compared to the what you can say. These valence electrons and nucleus. In the germanium, valence electrons are in the fourth orbit only. In the silicon, in the third orbit only it is existing valence electron. Third orbit means the attractive force from the nucleus is less, very high. The attractive force is very strong. It is very close only now. The fourth orbit means what happened now? The attractive force is somewhat weak. It is not much strong only we can say. Whenever the attractive force is not that much strong, we can come to the conclusion. The germanium can have the forbidden energy gap of less as compared to the forbidden energy gap of silicon I can say now. So in the silicon we can find forbidden energy gap the more because the attractive force from the nucleus to the valence electron is very strong. Here it is a less, the attractive force is less as compared to the what you can say, as compared to the silicon. That's why forbidden energy gap is here less only possible. This only explanation with atomic structure. Now you come back to the what? Not the diagram, already I gave it here now. Now I would like to explain here now this energy band diagram. In the energy band diagram, what you have to understand, but all the number of valence electrons are existing in this band. They are lying within the bond, and also the attractive force from the nucleus is very strong. The gap also existing, forbidden energy gap. When the conduction is possible, you can understand now. Suppose I maintain temperature is a 0 Kelvin. 0 Kelvin I maintain. At the time I cannot find any liberation of electrons from the valence band. No electrons will come out of the valence band. All they are going to lie within the bond, covalent bond. At the time no electrons reaching to the conduction band. The conduction band is empty. Conduction band is fully empty. When the conduction is possible, if there are electrons in the conduction band, without the what no electrons, so at 0 Kelvin what I did, I connected one external supply to this semiconducting material. Can you find any flow of current? Any conduction is possible or not possible? It's not possible. Why conduction is not possible? The temperature I maintained 0 Kelvin. At the time I don't find any number of electrons in the conduction band. The no electrons are in the conduction band. We cannot find any conductivity in the material. That is why the current passing through the semiconductor at 0 Kelvin is a 0. That is why it can act as an insulator. That is the final conclusion. In case I maintain temperature equal to 300 Kelvin, I maintain 300 Kelvin. What's going to happen in the material? At this particular temperature, this the particular temperature is just enough. This temperature is just enough to break the covalent bond. Otherwise, the temperature is just enough to make the electrons to liberate from the valence band. Once the electrons come out of this valence band, directly they are reaching to the what? No, conduction band only. They will try to move to the conduction band. Electrons will try to move to the conduction band. Once the electrons are reaching to the conduction band, you connect an external supply of very less, even 5 voltage or 3 voltage or 2 voltage or whatever it may be. Conduction is possible. Why conduction became possible here now? Due to existence of the electrons in the conduction band only, I can say. So, conduction band must be with some electrons to allow the conductivity. We got an idea. The information regarding the what now? This band theory. But what structure you can find in the semiconductors? Diamond structure we can find. Atomic arrangement inside will be diamond shape. Diamond shape means what structure exactly? Tetrahedron shape. Tetrahedron shape you can find inside only now. Even you have taken the germanium, even you have taken the silicon, you will find the diamond structure only now. Understand my point now? That is more important now. Next one. The next few more points I would like to give here now. But based upon the temperature, forbidden energy gap is changing, I said here already. Already I explained, based upon the forbidden but not temperature, forbidden energy gap is changing. How can you say when the temperature is increasing, the forbidden energy gap is reducing? Mathematically, can you give the formula for that? Means I can give the one formula. Based upon that formula, you can understand how the forbidden energy gap is reduced because of the increase of the temperature, you can say. The first point I can write, the increase of temperature, the increase of temperature reduces or decreases, reduces forbidden energy gap. Forbidden energy gap or energy band also we can write. Energy gap or energy band is allowed. Now here the formula which is to be written for this is Eg minus forbidden energy gap is calculated by the formula Eg naught minus beta into T. Generally the formula is applied. We need to use this formula only. The formula generally used. The formula is more important one, I can say. Understand my point now. This formula is more important. Forbidden energy gap at any temperature is calculated by this formula only. Eg naught minus beta into 2. Eg naught means what is the meaning here? Eg naught is nothing but the forbidden energy gap. Forbidden energy gap at 0 Kelvin. For 0 Kelvin only now. But I want to give Eg naught for the silicon. Eg naught is nothing but the 1.21 electron volts for silicon. For silicon, forbidden energy gap at 0 Kelvin is nothing but 1.21 electron volts. Beta value for silicon is 3.6 into 10 power minus 4. 10 power minus 4 they will use. But the T must be in Kelvin. T must be. Temperature must be in Kelvin. Kelvin. That's more important. Suppose you are given any centigrade. 30 degree centigrade means 30 plus 273. 273 whenever you are adding with the given centigrade temperature, you will get in Kelvin. So to find out the forbidden energy gap, it must be with Kelvin only, the temperature. Now catch my point. But what about for the germanium? For germanium, I can write like this now. Eg naught value for germanium is forbidden energy gap at 0 Kelvin is 0.785. 785. These are all in electron volts only. For germanium, I can say. That is for silicon, this is germanium only. And what about the beta value? Beta value is 2.23 into 10 power minus 4 they will use for germanium. These are all for germanium only now. So by substituting these values, you can get directly. Suppose you are asked when the temperature is nothing but the 300 Kelvin. Temperature is a 300 Kelvin. You find out forbidden energy gap for the germanium I asked. For germanium means what you will do? Eg naught 0.785 minus beta value 2.23 into 10 power minus 4 multiply with 300 Kelvin. You will get the value. In the same way for the silicon, you can use these parameters and the given temperature use it. You are going to get forbidden energy gap only. Understand my point now? Like that you can find only now. But anyhow, the formula is required based upon the temperature. Mostly where we can find, but I said just now I explained, only in the germanium you can find forbidden energy gap is less as compared to this silicon only. If you are getting any doubt, you put the different temperatures for the germanium, different temperatures for the silicon, and compare both, where you will find less gap you can identify. Understand my point now? That's very important. Next one. Now, common semiconductor elements we are using. Common semiconductor elements we are using. That is very important. Common semiconductor. Common semiconductor elements. Common semiconductor element. But mostly we are using the two types of the semiconducting material. One is a elementary semiconductor, The first one is a elementary semiconductor. And the elementary semiconductors are nothing but what we explained, germanium and silicon I explained now. Those two will come under elementary semiconductors only now. So examples for the elementary semiconductors are nothing but germanium and silicon. These are all come under the elementary semiconductors only now. And what about the next one is nothing but the compound semiconductor, I can say. Second one is the compound semiconductors. But all the crystal diode and the BJT and also the FAT is designed with elementary semiconductors only now. Where we are using the compound semiconductors? The compound semiconductors we are using in optoelectronics. The optoelectronics you can find photodiodes and also solar cell, like the different materials will come one by one now. There we are using the compound semiconductor. The compound semiconductor, what you can say, but I said already, all elementary semiconductors are with fourth group elements only. If the two different materials are two different atoms are combined, one from the third group, one from the fifth group, like that they will combine and they will form the compound semiconductor. I will give certain examples you can understand. Two element compound, but this comes under compound semiconductors are two element compound semiconductor. Two element compound semiconductor. This is also called as a binary compound semiconductor. But here what happens now, here the examples are nothing but what they are said to be two element compound semiconductor. Example I can give. Gallium arsenide we are using maximum in the optoelectronics, gallium arsenide. Gallium and arsenide, two different materials only now. Here also examples gallium arsenide, GaAs, gallium arsenide. But you know these two are not, it is not a fourth group elements both. The gallium is nothing but the gallium comes under third group. This comes under the third group only. Gallium comes under the third group element. Third group element means what is the meaning? The valence electrons of the gallium is 3 valence electron. And arsenide you got gallium arsenide. Arsenide is nothing but the fifth group element only. This comes under the fifth group element. Fifth group element. But the gallium and these two third group and fourth group addition is made, the two element compound semiconductor is formed. Even example gallium phosphide, GaP, gallium phosphide, and also gallium nitride, GaNa. Like there's so many examples you can give now. All these come under the two element compound semiconductors. And suppose you want to take the 3 element compound semiconductors, also possible. 3 element compound semiconductors are given like this. 3 element compound semiconductors. Three element compound semiconductor means 3 different group elements are combined. But examples only I will give now. Gallium arsenide phosphide. But these 3 elements combination on what it is forming, this compound element only now. And one more example is nothing but indium gallium, but like that it comes now. But like that it comes now. So many examples are there. When I say one example is enough only now. I can take now. And also 4 element compounds also possible now. Like that one by one is possible now. Anyhow, we are going to use elementary semiconductors only in our practical application. And also binary compound also we are using. Understand now. These are all the example. Next one more definition is more important. Atomic concentration. Atomic concentration. Atomic concentration. This is one more important one. Atomic concentration, that I can denote the symbol AC best. Atomic concentration. But what is that atomic concentration? How many number of the number of elements existing per cm cube, the number of atoms only exactly, the number of atoms existing per cm cube is said to be what? Atomic concentration. Mostly in the material, how many number of electrons are required, how many, what atomic concentration is exists, means total material, for total material you don't need to calculate. But practically they are going to consider per cm cube how many number of atoms are existing. Per cm cube only. Based upon the per cm cube you can find easily now for the total volume how many number of what atomic concentration is existing only now. Anyhow, here the definition what you can give for the atomic concentration, it represents number of, it represents number of atoms, number of atoms per cm cube. Per cm cube, how many number of atoms are existing, that we can say. Understand my point now. Suppose atomic concentration is a more and more atomic concentration is increasing. Then what happen now? Concentration of electrons also increasing in the material more only now. If the atomic concentration is reducing, you think it's so. At the time concentration of electrons existing in the material will be going down only here now. Understand my point now. Now the point what I wish to say, atomic concentration is a AC I said now. Atomic concentration is calculated by A naught into D, A naught into D divided by capital A. Generally this formula is used. The formula is used to find out the atomic concentration. You should mark up this formula. How this atomic concentration will be helpful in the problems also, I will explain clearly. You will get idea. Understand now. What is, yes, somebody is giving now. Dark Pavan. Yes, here the next one what I wish to explain here is what is A naught, where A naught equal to, I can write Avogadro number. It is given a name Avogadro number. Avogadro number. What is Avogadro number? A naught is a fixed value in the problems. Its value is taken as a 6.023 into 10 power 23. Its value is 6.023 into 10 power 23. There is a fixed value. And next one is nothing but the D. D is nothing but the density of the material. When the material is changing, density will be changing. Germanium can have some density value, you know. And the silicon can have the density of different. Tungsten, if it is taken, some other density value. One table also I will give in the next class, you can understand. Anyhow, D is nothing but the density of material only. Density, I can say. And the last one is the atomic weight. A is nothing but the atomic weight. Atomic weight. Atomic weight. So these are all the parameters are required to find out the what now? Atomic concentration. Atomic concentration, A naught into A naught is a fixed density changing, atomic weight changing based upon the change of the material, I can say now. Sir, I am going to find in the problems atomic concentration. But what its importance? Why we need to calculate atomic concentration? Atomic concentration main purpose is nothing but to determine the concentration of the electrons. But how we can find the electrons concentration? You please watch. I will give the clarity clearly now. By using this, you can determine by using this electrons concentration you can find. To determine the electrons concentration, electron concentration. But electrons concentration is denoted by symbol N. Already you have done. To find out the conductivity, we need to have the what now? Step by. Anyhow, in the what now? To find out the conductivity of the material, we are using N into Q into mu N. Concentration more important. Without knowing the concentration of electrons, we cannot determine number of parameters in the conductor or semiconductor or whatever it may be. So this concentration is calculated by atomic concentration. Atomic concentration. Without this atomic concentration, I cannot find concentration of electrons into number of free electrons. Number of free electrons means valence electrons. Number of free electrons. Number of free electrons. Number of free electrons per atom. Per atom. For example, you have taken germanium or silicon. Germanium I have taken for example. Can you find the electrons concentration, the germanium I asked? What you will do? Initially you need to find the atomic concentration for the germanium. For the germanium, you need to know the what now Avogadro number is given and what now density of the material is given, and also you are given the atomic weight. You will get the atomic concentration. Germanium contains how many valence electrons? 4 valence electrons. So atomic concentration is to be multiplied by number of valence electrons per atom, 4. Then you will get the electrons concentration only now. So the formula also very, very important. It is also very, very important. You must remember this formula also. You must remember this formula also. These are all very, very important. Understand my point now. But in this class, I will close. This is the class I will close now with this information. In the next class, you will find. The next class, you will find how to find out the atomic concentration for the different materials, and how to find the concentration of electrons. Everything you will get only now. Don't miss the class. The next class you try to attend. Next class is next class Sunday only now. Sunday at 4 o'clock it starts again. Every Friday, Saturday and Sunday at 4 o'clock I am going to start. I hope you are getting the satisfaction with the subject I taught here now. Thank you all.